Imagine being in now going into year 13, not knowing what turning point is, mate. It's not looking good. So turning point means gradient equals 0. And then it's saying show that this function has no turning points. So we differentiate. Here's a cheeky 4-mark question. We bring down the 3, knock 1 off the power. Bring down the 2, knock 1 off the power. And we have 3, mate. Now we basically have to prove that this can never equal 0. And we can do that very easily by calculating the discriminant. B squared minus 4ac. Hopefully it's going to be negative. So we've got b squared minus 4ac. So we've got 16 minus, what is that? 4 times 9 is 36, which gives you minus 20, less than 0. Therefore, no real roots. Therefore, f of x has no TP. Easy, nice. This question here was sent to me by my man Blakey, I think. I'm gonna call him Blakey on Instagram. Maths does Neil, innit? He said, "What about this one? How did you solve this?" Well, what was your first instinct to take logs on both sides? Maybe log base 5, log base 7, just general log, maybe ln. Well, it's actually easier than you think. What's interesting here is that the powers are the same. How can a power of 5 and a power of 7 ever be the same? Well, the only place where the exponential for 5 is ever the same as the exponential for 7 is when the power is 0. These are just 5 to the power of x and 7 to the power of x. So when the powers are 0. So actually, the only way this is true is if the power is 0 and x is minus 2/3. Thought you could trick me, mate. cheeky modulus question. Find the values of x such that this inequality is the situation. Now, any question to a modulus solving, you should be drawing a sketch. Modulus functions have a V shape. A modulus around it means that it's going to have a, well, I just said that, a V shape. Now, the way you basically draw these super quick is you just make this equal 0. That tells you where the vertex is. That's same as completing the square with quadratics. What's inside the bracket basically tells you the x value of where it has the turning point, right? Now, when you make that equal 0, you get minus 3/2. Then you just draw a V shape. Okay. This part of the line is obviously 2x plus 3 because it's a positive gradient. This part has a negative gradient, so it's the negative of this. The modulus basically took all the negative parts of the line and reflected it up. So this would be y is minus 2x minus 3. It's the negative of all of that. This crosses the y-axis at 3, yeah, because of the plus 3. And then 5 is over here. So what we need to do first is find the x values of where these two graphs meet. So the first one, we're just going to say 5 equals minus 2x minus 3. This one is when 5 equals 2x plus 3. Bring that here, minus the 5, so we get 2x is the positive 5 on the other side is minus 8. X is minus 4. Here we're going to get 2x is 2, x is 1. Okay. It wants to know when is the v below 5. Here's my v. Where do you see it being below 5? Above, 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 equal, below, 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 equal, above. So it's this part here is when the v is below the line. Those are these x values between minus 4 and 1. And it can't equal because of the inequality. Nice. Come on, Mike. Let's do some sigma notation, innit? So show that this sum equals some constant where k is a constant to be found. It looks quite weird, right? My first instinct is to rewrite the log as a subtraction. So you might be thinking, wait, isn't this further maths? The answer is no. They can ask these kind of sequences in normal maths A level. So if you're doing further maths, you might know about the method of differences. It's kind of like that. Well, in fact, it is that. I don't even need to say this. We're going to prove that. But I've seen this asked in normal maths A level, and if you've done enough practice, you've seen it too. Here, we're summing the first term up until the 48th term. So what we need to do is we need to find a pattern. So we're summing the first term. We sum in 1 here. So we get log. Just for this, guys, I'm not going to write base because that's long. Summing in 1, you get log 3 minus log 2. Sub in 2. So you'd get log quattro minus log 3. I can already see what's going on because we're adding all of these, right? These are going to end up cancelling. I'll show you one more. When you sub in 3, 3 plus 2 is 5. So 3, 4, 5, 2, 3, 4, etc. Boom. Boom. Yeah? Log 4 minus log 4. We're cancelling in this diagonal. Yeah? So that's never going to cancel with anything. But we need to think about the last line. Bro! N is 48. When n is 48, you get log 50 minus log 49. Now, which one of those would end up cancelling? Remember this diagonal? Log 5 would cancel with the log 5 in the next line. Boom, 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 boom. That log 49 is going to cancel with the log 49 in the line before. So we're left with log 50 and minus log 2. So minus means division. 50 over 2 is 25. Ah, interesting. 5 to the power of what is 25? 2! Nice. You're an hour and a half into your Waitrose interview. You're on question 69, and you see this question in it, Mike. What are you doing? What do you think most students are doing? They're going to factorize this, use partial fractions. They're going to integrate each term, spend half an hour. The Waitrose interview's over, and they didn't get the job. What should we have done? Not substitution. All of my students know that they could make a guess here. Shout out to everyone who knows my guess method. Because what I notice is that the denominator differentiates to something like the numerator. So I'm going to guess our favorite function, Mike, ln of the denominator. Check this out. If we differentiate that, then ln reciprocates the function. Then we differentiate the denominator to get the numerator. 2x squared goes to 4x minus ax minus 8. But we wanted x minus 2. So what we're going to do to both sides? We're going to do a quarter of both sides. A quarter of all of this gives you this. And there's your answer. So we ain't wasting time out here. Now we just need to sub in our limits. So we have a quarter. I'm going to keep the quarter outside of the square brackets. Ln x squared minus ax plus 3. Between 4 and 6. Now we just have to sub in 6 and 4. Okay. Subbing in 6, you get 72 minus 48 might plus 3 fish and chips and that. We got 27. Minus, what's that? 16, 32 minus 32. Oh, that's easy. They all just cancel ln 3. Okay, easy. 27 minus... Well, ln 27 minus ln 3, you divide them, so it's ln 9. So you get a quarter ln 9. But only an amateur would leave their answer like this. We notice 9 is 3 squared. We can bring down the 2. 2 times a quarter, half. Ln 3. Waitrose job secured. Nice. Only 9.2% of students could get this question correct. Let's do it. Prove log base 2 of 3 is irrational. There's a contradiction question. So the first thing we're going to do is assume log base 2 of 3 is rational. What does it mean for a number to be rational? It means you can rewrite it as a fraction. We need to set some conditions. In this fraction, both p and q are integers. Yeah, they're parts of the integers. And q cannot be 0. You can also say that p and q have to be co-prime. So P and Q co-prime. What does co-prime mean? It means that it's a fraction in its simplest form. Co-prime essentially means that the highest common factor between these two numbers is 1. Okay, the next thing we're going to do is get rid of log base 2. What's the opposite of log base 2? It's doing 2 to the power of both sides. So 2 to the power of log base 2 cancels. We're left with 3 equals 2 to the power of P over Q. The next thing is we don't like fractional powers. So we can get rid of that by raising both sides to the power of Q. By doing this, you're multiplying the powers, these cancel. And we're left with 3 to the power of Q equals 2 to the power of P. Now there's many ways you can conclude this. Powers of 2 are always even, powers of 3 are always odd, or you can literally just say the numbers 2 and 3 are also co-prime, so the only solution to this is Q and P being 0, which doesn't make sense because Q cannot be 0. So I think the best solution here is to say both 2 and 3 are co-prime, so only solution is P equals Q equals 0, which contradicts our assumption. Yep. Therefore, log base 2 of 3 is irrational. Only 88% of beekeepers could answer this 25-mark question, integrate cos x sin x e to the cos x. All right. Well, my first initial thought is that cos sine, I'm thinking about the double angle ID for sine. However, this is interesting because the power differentiates to what's down here. So this actually integrates to something quite nice. So I'm actually thinking about, what's it called? It is called integration by parts. So I am going to leave the first term. So leave. Integrate the second. Now to integrate that, I'm thinking about what differentiates to it. I'm going to try e to the power of cos x. What does that differentiate to? Cos differentiates to minus sine. Then this stays the same. But I wanted to integrate this with no negative, so I times by minus 1. It goes to just e to the cos x. No, minus e to the cos x. Minus the integral. Then we differentiate this. Cos differentiates to minus sine. Then we have the minus e to the power of cos x dx. All right, I messed that bit up, but it's cool. So we have minus cos x, e to the power of cos x. Minus minus is plus, so we have negative integral sine x, e to the cos x dx. And we've just done this. So this differentiates to something down there. So I can just integrate it directly. The working's here. So I'm guessing e to the cos x, that differentiates to minus sine x, e to the cos x. But I want the positive sign, so it becomes minus e to the cos x. Now with that negative there, the double negative just becomes plus. So we get minus cos x, e to the cos x, plus e to the cos x, plus c. Then from there, I guess you can factorize out e to the cos x, make it look pretty for the b's and that. I'm going to write this one first. 1 minus cos x plus c. Nice. One of the easiest integrals of all time is to integrate sec cubed. All right, first thing we do is we split up. Sec times sec squared. Now the reason we do that is because we know how to integrate sec squared. So I'm actually thinking about parts here. Bit of Lydian that. So leave the first term, integrate the second. Yeah, so leave the first term, integrate the second. What differentiates to sec squared is tan. Minus, differentiate the first term, that's sec tan. And then these two brackets are always the same. Okay, so simplifying, we have sec x tan x minus the integral of sec tan squared. Now, unfortunately, we can't do recognition here because tan differentiates to sec squared, so that's not going to work. I think the best thing to do is convert it all into the same function of sec. Tan, 1 plus tan squared is sec squared. So tan squared is sec squared minus 1. So I have sec tan minus the integral sec. What did I say? Sec squared minus 1. Okay. If I expand that bracket, I get sec cubed. Wait. I've gone in circles. Shout out Mac Miller, RIP, innit? We've gone in circles. I wanted to integrate sec cubed, but I've got sec cubed back into my integral. So this is a cyclic integral in that. I'm not writing dx because I can't bother. This and this, we can collect the like terms, right? The next thing I have to do actually is I have to split the integral. So minus sec cubed, minus the integral of this, then the double minus becomes plus the integral of this. If I add this over, I get 2 integral sec cubed x is sec x tan x plus the integral of sec x dx. Now, how do you remember what the integral of sec x is? First thing is this recip function, so ln. It's going to be ln modulus. How do you remember what goes inside the ln? You all know, or you should hopefully know, that sec differentiates to sec tan. So inside the integral is sec plus tan. So it's ln sec x plus tan x. So finally, when we divide by 2, the integral of sec cubed x is, should I just do all over 2? So sec x tan x plus ln sec x plus tan x all over 2 plus your constant. Nice. Not even joking, mate. Seriously, this is a 14-mark question. Let's do it. Got a substitution with limits. All right then. Where do we start? Well, I think the first thing we should do is change dx into du. Let's differentiate. Sine differentiates to cos. So dx, we're going to swap these around. Du over cos x is dx. The next thing I want to do is the limits. So these are our x limits. So u is sine pi over 6, which is a half. And u is sine 0, which is just 0. Don't force any substitutions. So you got a half and 0. 6 over, now this cos, I'm not going to change it. Nothing really directly substitutes there. 2 minus sine, which is u, times du over cos x. These two multiply together to make cos squared. And then we're going to change it to 1 minus sine squared. I've just explained that bit, cos squared, so I'm going to write as 1 minus sine squared. X, 2 minus u. And that then becomes 1 minus u squared. All right. How do we integrate that? It's looking like a cheeky partial fractions to me. So this, we're going to have to rewrite it. Well, let's take it separately. So we're going to have 1 plus u, 1 minus u, 2 minus u, a over 1 plus u, b over 1 minus u, c over 2 minus u. For this, I'm definitely going to use my cheeky partial fractions trick. So remember, you cover, if you want to find a, you cover the denominator. You say what u value would make that 0. U is minus 1. Then you look at this, you cover this up, and you just sub in minus 1. You'll get 6 divided by 1 minus minus 1 is dos, times 2 minus minus 1 is tres. So we get 1. And then for b, you would sub in u is 1. For that, you're covering this, yeah, that denominator. You're subbing in 1. You'd get 6 over uno plus uno dos times, we're covering that, 2 minus uno is uno, so tres. Then for this one, you're subbing in 2. So you get C, so covering that up, 6 over 1 plus dos tres. 1 minus dos minus uno. And that's gone, right? So we get minus 2. So our integral looks like this now. Let's integrate that. So this is nice and simple. Is ln of 1 plus u. This one, my guess, is ln of 1 minus u, ln of the denominator. But when you differentiate that, you get minus 1 over 1 minus u. But we wanted 3, so you're going to times by minus 3 on both sides. So we get minus 3 ln of 1 minus u. This one, we're thinking about ln of 2 minus u, which when you differentiate that, on the top you get minus 1. But they wanted a 2, or minus 2, so you're just going to times by 2. So we get plus 2 ln 2 minus u. Now, I haven't written it, but the question wants you to leave your form as a ln 2 plus a ln 3. So they're keeping it separate. So I feel like the way we should do this then is just sub in a half as is and try and simplify along the way. So when you sub in a half, you get ln of 3 over 2 minus 3 lots of ln half plus 2 ln 2 minus a half is 3 over 2. Because then these are going to be able to these two are going to be able to combine. So we have that minus, when you sub in 0, you get ln of 1, that's 0. You get ln of 1, which is 0. Here, though, you get 2 ln 2. Okay, actually, I can see what's happening here then. So this plus this gives you 3 ln 3 over 2. Now this you can actually rewrite it. So ln of a half is ln of 2 to the minus 1, which when you bring down you get plus 3 ln 2. That we've combined, minus 2 ln 2. Now we're not done yet because we need to get it all combined nicely into a ln 3 and a ln 2. So how's that going to look? Well, this we need to split it into a ln 3. The division means minus. But with that coefficient, it's going to become 3 ln 3 minus 3 ln 2. So that's that. Then this minus this is just ln 2. So we're left with 3 ln 3 minus 3 plus 1 is minus 2 ln 2. And that is our 14 mark as the question done. Nice. Some brother who's not even following me asked me to differentiate this. I'll just do it anyway just because I'm a nice guy, innit? So to differentiate this, we can clearly see we have powers. It's a power function, or you guys know I like to call it a Pavan function. And instead of writing the whole thing again, you're going to bring this up. This power is going to become minus 4. All right. So we've got minus 4. How do we differentiate something like this? Well, to differentiate Pavan functions, you differentiate what's in the inside first. So whatever that differentiates to is going to come on the outside. Then we bring down the power, knock one off the power. So we've got to figure out how to differentiate this. I see a root. I don't like that. I'm going to write that as power half. So around this whole thing, we have power 1/2. We need a square bracket here so we can clearly see the differences between everything. Okay, so I don't know how much space I'm going to have, but let's just focus on this. Yeah, so we're going to differentiate x is 1. Easiest part of the question, I guess. Plus. Now, how do we differentiate this? Forget about everything else. Here, we have another power function. Here we have something on the inside to the power of 1/2. So differentiate this, we need to differentiate what's on the inside first. 4 goes. Here, we have another power function. We have to differentiate this. So differentiating what's on the inside first, we get 2x. So we get 2x. And then we have to bring down the power, knock 1 off the power. So multiplied by bring down the 3, knock 1 off the power. Okay, now let's just remind ourselves what we even just did. So we differentiate this. Then I was focusing on differentiating this bit. The 4 disappeared. I have just differentiated this. Yeah? And that's this. So, having just differentiated this, I'm going to put a bracket around it. I now need to bring down the power, knock 1 off the power. So, I'm going to get times, bring down the half, and then I knock 1 off the power. That'll become minus a half. Okay, so with these kind of questions, just keep reminding yourself what you even just did. So, the whole thing we're trying to do here is differentiate what's on the inside. I differentiated the x. I was in the process of differentiating this. Yeah, so I brought down that power, knocked 1 off the power, but then I had to differentiate what was on the inside first. Yeah, so I differentiated the 4, it's not there, and I differentiated this, which is this. Yeah. Now another thing that happens here, before I look at the overall function, is that this half cancels this 2. Okay, how can we write this neatly? I guess we have all of this is all in one line. I guess I could put this in like a fraction maybe. So we're going to have 1 plus 3x, x squared minus 1 squared. Then this can come down into the denominator because it's power minus half. That will come down as a negative, but then we can write it as a root. 4 plus x squared minus 1 cubed. Alright, so that is the differential of what's on the inside. Okay. Now what we need to do is we need to bring down this power and knock 1 off the power. So we are actually going to get, let me put the plus 1 here, make it look neat. So we can bring down that minus 4. And that is going to multiply by everything on the inside, but knocking 1 off the power. Yeah, so bring this down, times all this to the power of minus 5. Now, the minus 5 will basically bring it into the denominator, power 5. So we're going to get all over all of this to the power of 5, because I brought it into the denominator. So I'm going to get x plus, this I'm going to rewrite back as root 4 plus x squared minus 1 cubed to the power of 5. And that, can I clean that up even more? The answer is, I guess, yes, by like timesing top and bottom by root 4 plus x squared to the minus 1 cubed. Now, is it necessary in this case? Not really, just because they wanted us to differentiate. It seemed like a bit of a troll question, I can't lie. But yeah, I guess you could times top and bottom by the root of 4 plus x squared plus 1 cubed. It doesn't really make it look any nicer, but yeah, I'm happy with that. 13 marks, mate. Can you really afford to mess up such an easy question? So, find the area between the tangent to the curve at A, the curve itself, and the x-axis. Now, they did say in the question that A is where the curve crosses the y-axis. So the first thing we're going to obviously want to do here is, well, actually, there's a lot of things going on. We need to make a plan. Most likely, we should just work out what the equation of that tangent is, because the strategy we're going to use here is to do the triangle minus this area. Now, this area here is the area under the curve between 0 and wherever it crosses the x-axis. So it's good with these questions to make a plan. So let's just work out what the equation of the tangent is. So here's my equation of my curve. To work out the equation of the tangent at this point, we're going to have to find the gradient function, dy by dx, which is already worth a lot of marks in itself, just differentiating this. The 2 goes, we get minus 1, so that's differentiated, minus 2x. Okay, now what's the x value here? X is 0. So dy by dx when x is 0 is just minus 1. Okay? Then we're just going to sub in the coordinate. Now, A has a coordinate x is 0. When you sub in x is 0, you get 2. Okay, so we know the y-intercept. So actually, we know immediately what the equation of the tangent is. Y equals mx plus c. So just minus x plus c. I want to find out where it crosses the x-axis. When you make y equals 0, you just get x is 2. So I'm trying to save space here. So that is 2. We have 0 and we have 2. So we are going to work out the area of the triangle, which is a half of the base length. Half of 2 is 1 times 2, just 2. Okay, so that's the area of the triangle. Now we're going to work out the area of the curve between 0 and wherever this point is. So for that, we're going to have to make this equal 0, right? So we're going to move that all to the other side. We get x squared plus x minus 2 is 0. X, 2, 1. To make plus 1, we need plus 2 minus 1. So x is 1 and x is minus 2. So minus 2 is going to be here. This is just 1. So we're going to integrate this curve between 0 and 1. Or 2 minus x. Try not to sneeze. That. Okay, so we get 2x minus a half x squared minus a third x cubed. 0 and 1. 2 minus a half minus a third. Something in 0 is just 0. You actually need to show that in the exam. You need to show that minus 0. Minus a half minus a third. Mate, what is that? 12 over 6, isn't it? So I'm going to do a common denominator. Times some by 3. 3, 6, 2, 6. So 7 over 6. Minus 0, so just 7 over 6. So we're going to do the triangle, which is 2 minus 7 over 6. 2 is 12 over 6. So I get 5 over 6. So there's loads of mini parts here, which is why it all totals up to 13. And I'm actually not making it up this time. Nice. I can't stress enough how many different skills are going to be involved in this question. So before you do anything, save this for your revision soon, mate. So this is going to involve exponentials, differentiation, and graphing. So prove that 8 to the power of 2x minus 4 to the power of x minus 1 plus 2x has no stationary points, meaning that the gradient function cannot be 0. Now, should we differentiate it first? Probably not, in my opinion, because I'm thinking, look, these are all base 2. And usually what we always do with these kind of questions is we convert it, right? So 8 is 2 cubed to the power of 2x minus 2 squared to the power of x minus 1 plus 2 to the power of x. So we get multiply 2 to the power of 6x minus 2 to the power of 2x minus 2 plus 2 to the power of x. Now, I guess I want to break this off before I differentiate, just make it a little bit nicer. Well, arguably nicer. 2 to the power minus 2 is a quarter, so maybe you could say this isn't even nicer. But I think when it comes to the differentiation part, it is. Okay, so how do we differentiate this? So differentiate exponentials. Exponentials in general stay the same, but we always differentiate the power. 6x differentiates to 6. Now 2 to the power of differentiates to ln 2 times the exact same function. Yeah, now if you haven't done differentiation yet, you should definitely be saving this video because it's an important one. So differentiate the power. 2 times a quarter is a half. Then remember, ln 2 times the exact same function. And this is just going to be my ln 2 times 2 to the power of x. Can you guys see that? Yep, cool. Now, we're going to make that equal 0 and prove it doesn't have solutions. Now, the beautiful thing about this is that everything has ln 2, so we can divide by ln 2. I can actually divide by something else. Remember, 2 to the power of x is not allowed to be 0. It's bigger than 0. So I can actually divide through by 2 to the power of x as well, which reduces all of these powers by x. So I'm going to be left with 6. Dividing that by 2 to the power of x would be 2 to the power of 5x minus a half. minus a half. Dividing that by 2 to the power of x is just 2 to the power of x. Plus that divided by 2 to the power of x is 1. All right. Should we times through by 2? So we get 12 to get rid of this. 2 to the power of 5x minus 2 to the power of x plus 2 is 0. Guys, if you're finding today's video useful, hit the heart button and save this video for later revision. All right, now we somehow need to prove that cannot be 0. So, let's do a conversion. Let's let u equal 2 to the power of x. So we're actually looking at 12 u to the power of 5 minus u plus 2 is 0. And you might be wondering, wait, we don't know how to solve quintics. And actually there's no such thing as a quintic formula to solve, nor can our calculator, for that reason, solve that. So we need another strategy. We need to prove that that does not have any solutions, or at least solutions that we're interested in. And this is where we're going to go back to year 12. We're going to use a graphing strategy here. So what I'm going to do is I'm going to move this to the other side, and I'm going to see if I can find what type of solution it is. So what I'm going to do is I'm going to sketch this function. Now a quintic looks exactly like a cubic, like this. In fact, it will be really narrow. Now u minus 2 will cross the y-axis at minus 2. It will also cross the x-axis at 2. Now you might be wondering, how do I draw it? If I call that 2, if you sub in 2 into here, you're going to get 64. So if that's 0, yeah, and that's 64, it's going to be huge, yeah? It's definitely not going to intercept it at all. And that, to be honest, by this, it makes complete sense. But what you notice is that there's one solution which is negative. Okay? So there's one negative solution. Now, why is that an issue for us? Well, it's to do with the fact that if u is negative, so the solution is u is less than 0. But this is a problem because 2 to the power of x cannot be less than 0. Remember, u is this. However, 2 to the power of x is bigger than 0. Therefore, there are no real solutions to this problem. Therefore, no stationary points. Not pints. But anyway, that's how we do this problem. There's a lot of skills involved in this one. So yeah, like I said, make sure you like this video, save it for later. And if you're interested in my courses, then head to myheadspace.co.uk to learn more. Nice. On today's video useful and you want to learn more maths content with me, then head to myheadspace.co.uk and learn more about our courses. Can you really afford to not be able to answer this easy 7-mark question, mechanics question? So you got this diagram. I mean, if you guys know in mechanics, they just write a load of rubbish, but this is the main information. We got a box, 3 kg, it's being pulled up on a rough plane, coefficient of friction 0.3, find the acceleration. All right, so how do we annotate our diagram? Well, it's being pulled up, so you indicate which direction your acceleration is going, and this side our forces, so it's 3 kg. Use long loins, the weight will be 3g. We're obviously going to resolve our forces. This would be 20. So this would be 3g cosine of 20, the adjacent side in our right angled triangle. This would be 3g sine 20. And we don't need to use that anymore. We have our reaction force. R does not just equal this, because we also have to resolve this as well. So this force, which in the question said was a rope with tension 25, is pulling the particle up the plane. So it's pulling up the plane, and also it's trying to pull it out the ground. Yeah? So we're going to resolve this. This is the adjacent side. It will be 25 cos 30 and 25 sine 30. And that's done. Don't need to deal with it anymore. The last thing we have to discuss is the coefficient of friction, well, just friction in general. So it's being pulled up the plane. Friction's going to oppose that. Now, friction is going to be at its maximum here because it's moving. Yeah, so we have mu r. Mu is 0.3 times whatever r is. All right, nice one, Mike. This is now easy. So the first thing we're going to do is we're going to look out and into the ground. What's pointing out the ground? We have r and 25 sine 30, which is a half, to be honest. Now, when you do these, I just do a little tick on the forces so I know I've used them. Is 3g cos 20. So R is 3g cos 20 minus 25 sine 30. Nice and easy. So these are all done. Now we're going to look at up and down the plane. So because it's moving in this direction, we're going to do F equals ma, but F is the net force, right? It's the positive forces. This is obviously the more powerful force because it's moving in that direction. So the net force is this. Take away the forces that oppose that. So it's going to be 25 cos 30 minus, you can write minus for both, 0.3 R minus, so let's start ticking these off, 3g sine 20 is the mass of the object 3 times A. And then boom, nice and easy, mate. All you got to do now is just divide both sides by 3. Plug that in, mate. And you get A is like 2.4. Quick mathematics. Nice. Right, my brother J Hib Liz on Instagram, man, like from Kenya, sent me this question. Find the value of x in this equation. Okay, so where the x is here. Now the bases are different. We need to use the change of basis formula so that we can bring everything together. So all of these should either be log base 2 or log base 3. Well, what's the easier one to change to? I'm looking at this. Log base 3 of 8. If that was log base 2 of 8, that would actually be a much easier calculation to do. Because log base 2 of 8 is 3. It's saying 2 to the power of what is 8. So here we have to use the change of basis formula, which is actually very simple. How does it work? I want this to be log base 2 of 8. You just rewrite it. But then you divide by log base 2 of the old base. Okay. Here, that's already log base 2. This is also log base 2. Here again, I want that to be log base 2. So just write it. Log base 2 of x, but then you have to divide by log base 2 of the old base. Now the next thing I'm going to do is I'm going to get rid of all of these denominators. So, and also this is 3, right? So 3 plus timesing through by log base 2 of 3. This would be log base 2 of 3 times log base 2 of 7.2 is that times log base 2 of 3 times log base 2 of x plus, that's gone, right? Log base 2 of x. Now these are the same, right? So we can collect the like terms. This just is what it is. 3 plus log 2, 3, log 2, 7.2. Factorize out log base 2 of x. We get log base 2 of 3 plus uno. Then we're going to divide by that bracket. I'm just going to do it now. Log base 2 of 3 plus 1. Okay. Then we rearrange for x. So that's log base 2. What's the opposite of log base 2? It's 2 to the power of. So you're literally going to do 2 to the power of this whole thing. And that, my guy, J Hib or something, is your value of x, and I'll leave it to you to type it in the calculator. Nice. 100% of wastemans could get 8 marks in this question. Okay, so we've got dy by dx is all of this. Show, that's the situation. I love a show that question because then, as an examiner, it just makes life really easy to mark, innit? You just look at the answer. So you get all the y's to the left side and all the x's to that side, innit? So it's all multiplication. So we're going to multiply by dx, and we're going to get this to this side by division. So we're going to get 1 over y minus 2, y plus 1 dy is x squared dx. And we're going to integrate both sides. To integrate this, we need to use partial fractions. So here we can use my cheeky trick in that. So, to find A, let's do it here. To find A, you look at the denominator and you say, what would make that denominator equal 0? Yeah, it'd be 2. Y is 2. So you cover up that y equals 2 on this side and you just sub in 2. Yeah, remember that's what that makes that 0. So you get 1 over 2 plus 1, which is 1/3. For B, yeah, what makes that equal 0, mate, is minus 1, isn't it? So you cover that up, sub in minus 1. You get 1 over minus 1 minus 2 is minus 1/3. So here you are integrating A, which was positive 1/3, over y minus 2, minus 1/3 over y plus 1 dy is the integral of x squared dx. Now another thing we can do here is we can factorize out the third. Yeah, I'm going to write the third on the outside and then rewrite all of this as 1. I mean, you could keep it in, but I don't think it's necessary. Because these integrals are really simple, right? So we get third of ln of the denominator. Now you guys always know that I put my constant of integration within the ln. Minus ln of y plus 1 is 1/3 x cubed. And there's another reason why I factorized out a third. I knew this would happen. This is why I put the a within the ln. We're going to divide. Then we're going to have one term on each side. We can cancel out the ln nice and easy, white. So we get ln of a y minus 2 over y plus 1 is x cubed. E to the power both sides. Cancellations. And we basically have our answer, right? So we have a y minus 2 over y plus 1 is e to the x cubed. Then you just divide by a. So can you see they've got their constant of integration there? We divide by a. Now, technically speaking, when I divide by a, I need to rewrite it. You know, 1 over an unknown constant gets absorbed as a new constant. Here I'm going to use b. Now, it doesn't matter that your constant looks different to the questions. They're just using the alphabet. But as you go along, you should be changing. Sweet as a nut, mate. Some of the further mathematicians of Lund Gang wanted me to answer this really easy 1-mark reduction formulae question. So, in or Ian is the integral of e to the power of 2x sine to the power of nx dx. Show this beautiful thing is true. Well, this, as I've highlighted here, is integration by parts. Now, when we do integration by parts, you guys know I like to say LIDI, is you leave the first term, integrate the second, differentiate the first, integrate the second. In this orientation, I don't want to leave this and integrate this because I don't know what sine to the power of nx integrates to. So in fact, I'm just going to switch them around. This is going to be the one that I leave. And I'm going to write like this, sine x to the power of n. Integrate this. Now I know you guys love substitution. And a lot of you would do substitution to integrate e to the power of 2x, which is kind of peak. But that just becomes this. So we leave, integrate, differentiate. So differentiating this, you differentiate the angle is cos. Bring down the n, so it's n cos. Then knock one off the power. These brackets always the same. Okay, now cleaning this up, this n and the half can come outside of the integral. So we get n over 2. We're going to have to do parts again, because what is that? I don't know what's going on. So, let's do it. So, doing our LIDI. I think I might need more space, because we're going to differentiate. Because we're going to leave this, right? Cos x, sin x to the n minus 1. We leave the first term, integrate that, which we know is this. But we have to differentiate this. We can only differentiate this using product rule. Differentiate the first term, cos differentiates to minus sine, times the second term is sin x to the power of n minus 1, plus, differentiate the second term. Well, you differentiate what's inside. I'm going to do this kind of all in one. Just listen to what I'm saying, yeah? Differentiate this is cos, Then you bring down the n minus 1. So you have n minus 1 cos of this to the power of n minus 2, because you're knocking 1 off the power. But then you're timesing by this cos. So it's actually cos squared. So you have, bring down the power, n minus 1, cos squared x. Then we knock 1 off the power, sine x to the n minus 2. Okay, that's the differential of the first term. Times the second term, half e 2x dx. Okay, this simplifies. That becomes negative sine x to the power of n because you add 1 to the powers. This half can come outside. Alright, so we have a half e to the 2x cos x sine x to the n minus 1. Yeah? I'm going to expand all this in and separate the integrals. Yeah? So we have a... This is minus sine x to the power of n, like I just said. The minus half, with the minus, becomes plus half integral of sine x to the power of n times e to the power of 2x dx. Then this times this and this. This actually is a constant, right? It can actually come out with this. It becomes minus m minus 1 over 2 integral of cos squared. Actually, if I'm going to rewrite it back as this, I'm going to rewrite cos squared as 1 minus sine squared. Times sine x to the n minus 2 e to the 2x dx. We're going to have to multiply both of those terms in. This is Ian, right? Yeah, so I have a half e to the power of 2x cos x sine x to the n minus 1 plus a half of Ian minus n minus 1 over 2 integral. Multiplying these in, you're going to get e to the power of 2x, e to the power of 2x, sine x to the power of n minus 2, yeah, minus, when you multiply these, you're going to add the powers. 2 plus n minus 2 is just n. So we get e to the power of 2x, e to the power of 2x, sine x, power of n dx. But that's Ian again, right? And this is this, but with n minus 2. So we get a half e to the 2x cos x, sine x, n minus 1 plus a half Ian minus n minus 1 over 2. Now this, remember, is Ian, but with n minus 2. But then when you multiply with this, it becomes plus m minus 1 over 2. That is Ian. But all of this needs to go back into here. And that all equals in. Oh, man. So, we have Ian. That integral is this. Half e to the 2x sine x to the power of n minus n over 2 times all of this. Times that by minus n over 2. Minus n over 4. Times that by minus n over 2. Times that by minus n over 2. Times that by minus n over 2. Hey ho, I better not have made a mistake here. I'm timesing through now by 4, right? If I times everything by 4, that was a half, right? Yeah. Times everything by 4. Times everything by 4. times everything by 4, times everything by 4. This is calm. This is what it is. In fact, that's probably going to give me something like this. I'll double check in a second. It's bringing all these ions. Now the ion look, that matches up. Calm. What's the time? Oh God. I got somewhere to be, bro. So what was I doing? That. Okay, this I think I'm going to deal with first. 4in. Here I can factorize out e to the 2x. What did I want to factorize? Yeah, you always factorize out the smallest power, right? Because when you take out e to the 2x, you're left with 2. Then you subtract the powers. N minus 1 is just 1, so you get sine x. Minus, you took that out, so n cos x. Yes. Then you have minus n in plus n, this I'm not changing, right? Minus n squared in plus n in, which cancels. And then this, we're going to bring here, because then we have n squared in with this. Then when you factorize it, you get this. How much below can I write at the moment? I don't know. Hopefully you guys can see it. So this is going to come with this. Then you're going to factorize out in, and you get n squared plus 4 in is that plus 2 sine x minus n cos x times sine, how did I write? E to the 2x sine x to the power of n minus 1. And that's proved. Yeah! Come on, let's go.